Okay, so we've got this chain complex, and it comes, you know, if I want to be really careful, what I should really say is this chain complex, we can use this notation. A lot of times people use notation C sub star to just indicate a general complex, so that, but it really depends upon the Morse function f and the gradient mark character v, right? And of course there's a boundary star, which also depends upon v. Well, actually the C star only depends upon f, right? Because the generators are, as a complex, just a list of groups, its generators just at the critical points, but then the boundary map depends upon v. And so, but I want to suppress that notation, but I just want to say, okay, suppose we have, suppose C star, boundary star, come from some at v, and we do one surf move. So this is the ways in which f can vary. So these are going to be hand slides, bursts, and deaths. We already figured out that finger moves are just, we don't have to worry about them. They don't change anything. One surf move, we get some f prime, b prime, giving the chain complex. That's called C star prime, boundary star prime. Right? And then the goal is we want to show that this move induces a chain homotopy equivalence between the two complexes. C star boundary star to C star boundary. And I'll remind you what chain homotopy equivalence means. So that means that we have, let's see, what do we want to call it? It's called phi. It's really for phi star. What that means is that you have your chain complex Cn, Cn minus 1, Cn 0, and all your boundary maps, and then you have your other chain complex Cn prime, Cn minus 1 prime, Cn 0 prime. And then you have some maps going this way. Actually, you have, what it really means is the chain. So this is a chain homotopy equivalence, which actually means there's also a map going the other way. And which are, so that okay, this will be phis, phi sub n, minus 1, phi1, phi0. And chain homotopy equivalence, what it means is there's also an inverse up to chain homotopy, so there'd be some other C sub n, P sub n minus 1, T0, and the composition of them is not supposed to be the identity, but it's supposed to be chain homotopic to the identity, which let's sort of, let me say, both compositions CI. So first of all, the phi i's are supposed to commute with the boundary map. So the whole thing, everything commutes. And then Ci composed of C star, phi star, and phi star, C star. The best way to say that is that, well, there's got to be some other operator going diagonally. I don't want to write all that down right now. If you haven't seen it before, we'll come to it. But so if you haven't seen it before, just the point is that these are going to induce maps on homology, which are the identity. So that's why I say these induce the identity map. That's really all we care about. So it means up, you know. And so they both induce the identity maps on homology here and homology here. What it means, so you know, to get a map from there to there, a map from there to there, and so on, and then you can look at how the homology is the kernel, not the image. You can look at how, so these, because of things commuting with the boundary maps, kernels go to kernels and images go to images. And so then you want to know that the induced map is not just an isomorphism, but I mean actually the identity of it. Yeah. I think I said, I don't think I said anything stupid yet. All right. So, but this is pretty easy in this case, I guess is what I want to say. In general, like algebraic topology, chain homotopy equivalence is going to be pretty elaborate. But each of these, the way, for each of these two surf moves, the ways in which these things, these chain complexes depend upon the ways in which the chain complex changes is very straightforward. So we'll just do them each by themselves. So let's do the birth depth first. So the birth depth happens, so we get a new, let's do a birth, which is the inverse. In fact, we'll do birth and death simultaneously. They will be the phi and the psi, each be the inverse of the other. So birth, let's say, is going to produce an index I and I minus 1 pair, cancel. Right? So then that means that we have the chain complex. So we have Cn dot, 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 and then here in the middle we have, let's do it, we have Ci plus 1, Ci minus 1. Just for good measure, you put some extra stuff at the end just to make sure you sandwich them on both sides by something to make sure nothing, you haven't forgotten anything that's happening. And then the prime button, everything is the same, except when you get to Ci prime, you have Ci, and then you have direct sum with another generator. Let's say the new, call this one Q, call this one P. These are the critical points. So we have a new copy of Z generated by P, and then we have Ci minus 1, direct sum copy of Q generated by P. Space here. Let's try to hard them up. And so what's the maps? The maps are the identity here. Here. Oh, and what's the extra? How does this boundary map relate to that boundary map? This is some boundary map, boundary I, and this boundary map is boundary I plus direct sum. The thing that I'm just going to write it this way, the map that sends U2. That's it. Right? Because this generator, the boundary of this generator, there's exactly, after a birth, there's exactly one flow line from critical point P down. I got it backwards. I was trying to use Q for higher index things. Okay. So this notation makes sense to everybody. And so the map going this way should just be the inclusion, right? And the map going this way should just be the inclusion of that factor. And then the map going this way should just be the map that sends Q to 0 and P to 0. Okay? So the map going this way, that goes to, it's just, that's right, it's the identity plus Q goes to 0. I mean, you probably realize I'm making a hash out of something kind of simple, because if you look at this, the whole point is,
You just compute homology.
if you just want to compute homology, right, then nothing changes, no kernels or images change up to here, right? Here you haven't added anything new to the kernel, right? Because Q is not in the kernel of this map. So you don't have to worry about it. So you haven't changed the homology here. And here you do have something, I should say what, yeah, in fact, I do sort of have to say what this boundary map is, right? So this boundary map is boundary I minus 1 that directs on the map that sends p to 0. Okay? And then this boundary map is just the inclusion. This is just boundary I plus 1. And just included the CI, so you just ignore that, right? Okay, so then this one, anyway, so therefore P is in the kernel, but it's also in the image, so it's good. So it doesn't mean either. But you want to be a little bit more careful about that because that just says that you haven't changed the homology up to isomorphism, and we want to know that somehow in a natural way you haven't changed the homology. But it's really not. It's still basically the same idea. It's basically the same thing. So that the map going this way is the identity plus P goes to 0. P goes to 0, and anyway, the point is, the first thing is to check that these are chain maps, right? And to check that these are chain maps, that's actually the only part of this calculation that's non-trivial, right? To check that these are chain maps means that if you start here, include this here, and then take the boundary. Well, if you include this here, you don't ever see Q's, you take the boundary, so this map is just, the composition this way is just the inclusion of its boundary I followed by the inclusion there, which is precisely this thing, right? So the commutativity is trivial to check, and then, so these are both, and in the other direction it's easy as well, so they are all chain maps, right? I mean, you might worry that we're just killing Q and killing P. Why are we losing all this information? Why do things still commute? But it's precisely because, well, let's check this way. So here, Q is killed and then sent to the boundary. Here, Q is sent to P, but then P is killed. Okay? You probably want to be careful that you have to be careful about these squares and these squares, but it's not hard. And then the compositions. Then we want to check that the compositions are chain equivalences. This composition is the identity, right? So that's obvious. And the compositions the other way are not the identity. The composition the other way is projection. Is sends Q to 0, right? So when this thing is Q goes to 0, and this projection here is P goes to 0. Okay, and so those are not the identity maps by any means, but they induce. So now you want to check that this map from this chain complex here back to itself and just kills Q and P. You want to check that that induces an isomorphism on homology, and that's basically what we just said.
The identity.
The identity, right? It induces the identity, not just an isomorphism, the identity, exactly. And so that's exactly the point is, P is not in homology anyway, it's killed by homology, Q is not in homology, everything else is left unchanged, so it really does induce the identity. So I won't write anything else down like that. So that's and the depth, well, depth would be just going the other way. So now we'll do the Hammond slide, which is really more stuff.
Oh, but I guess when you go the other way, the induced maps are the identity on the chains, so it's easier.
I mean, yeah, right. So, well, this composition. Well, what I was saying about birth or death being symmetric, right, is if I was doing a death, then this would be my first chain complex,
Right.
and this would be my new chain complex. But the situation is completely symmetric. So this composition are just the identity on the chains,
Right.
exactly. All right. So as the slides. So now we have two handle slides. We have two critical points of the same index, and one's going to slide over the other. Okay, so we have, let's say, P and Q, critical points. It's I, and then Q slides over P. So let's do this, let's label the new, so P sort of doesn't change, and Q becomes a new critical point, we'll call it. I mean, in some sense it's the same, but it's a different function, so a different thing, so that, you know, become Q prime. So we have P and Q, P and Q go to P prime. All right, and we want to say what does that do to the boundary map, right? And what I claim is that so the claim is that the boundary of, so when P's, nothing's happening with P, so we don't change the boundary map of P at all, right? But we're going to change the boundary map to Q. My claim is the boundary of Q prime equals the boundary of Q plus or minus the boundary of P. So I'll do my usual thing of deferring the proof of the claim. Let's see if we believe in that. If you believe that, then and I'm sorry, we also have to think about the incoming boundary map, right? We have CI plus CI. We have to think about right. So what do I want to say? I want to say that I have to give an example. Well, what I really want to say is that if you think of these as, if you think of each boundary map as a matrix, right? Because we have preferred generators, right? And if you think of each boundary map as a matrix with respect to these preferred generators, then let's actually be kind of careful about it. So I've got CI minus 1, CI plus 1. Okay. And so if I have two generators, P and Q here, which I'm going to think of as basis elements, right? And then I have all of my basis elements, you know, A1 up to AK, here, and B1 up to BJ here. And here I have lots of other basis elements as well. But I just want to focus on the part that corresponds to this. So each of these matrices now, so let's say I have, the point is that I just want to figure out the dimensions of these matrices. If I'm mapping to RK, right, then I have to have K columns for ZK, right? So this is going to be let's suppose there's L of these, right? And then I'm going to have an L by K matrix here, right? So where each column is the image of is the boundary of one of these things. Okay, so I have one column here, which that column will be boundary of P. And I have another column here, and that column will be boundary of P. Right? That's what this boundary map is. Right? And then here I'll have I'll have L will be the size, so I'll have L by J. Okay? And now this row, it'll be a P row, which is the P, you could write it, it's just the P component of the boundary map, right? And then I have another row here, which is the Q component, right? And so I claim that the way that the boundary map changes, I'm going to CI prime. And I'm going to CI plus 1, which has all the same generators, and a CI minus 1, which has all the same generators. So those are gonna look just like this. This is gonna have all the same generators, except it's gonna have a new generator one called Q prime. And what we've done is we've added the P column to the Q column. So the way this matrix is related is that we add, this is this is the sum of the P column and Q column. So we've done an elementary column operation on that particular, so that's consistent with what I wrote here, right? Now, what I'm sort of hemming and hawing about is the best way to explain what I want to do here, which is we add the, I'm going to add the Pth row to the Qth row. Okay. And so here, this is the P, this is Q, this is P, and this is Q, Q prime, and this is the sum of Qth row and Qth row from the previous one. So I think the best way to say that is that for any, let's say, B, any critical point B of index I plus 1, we can take the boundary of B and we can look at it, I'm going to say this, dotted with Q prime, by which I mean the Q prime component of the boundary of B. And I frame that's equal to the boundary of B, that dotted with P, plus the boundary of B. Maybe I should put the boundary, okay, this is what I should have done. Plus or minus the boundary of B dotted with Q.
So your P and Q there are like the standard basis.
My P and
There's
Q,
a 1 and the,
my P and Q are particular critical points, which
Yeah, but when we talk
are
about it as
standard
a
basis.
vector.
When I say dot,
you mean
what
like,
I mean is pull out the Q,
okay.
each one gives a component, right?
Right, so it's
There's
like
the coefficient on it, so it really is like dot product and standard basis, I think, right? I mean, this is a way to sort of reference the, if you want to reference the certain component of something that's, okay, is that clear?
So how is that? Isn't that?
This
a
is
more
not
general
saying that-
statement than the one before.
Huh? It's not the same thing as, well, these are different boundary primes. This is the one, okay, this is boundary primes of I, and this is boundary primes of I. I need to describe how the two different, there are two different boundary maps that are changing. And that's what I have to be careful about. And maybe another way to say this would be that the adjoint of this map changes by, you know, if you like, you could say boundary prime I plus 1 star equals, you know, of anyway, I don't know what to say. But there's another way to say it for the adjoint, which is looks, you know, how the formula looks just like this. Okay, the adjoint. Because the adjoint is just the transpose. You know, the whole point is it's easy to say in terms of matrices, here you have the columns, here you have the rows. Okay? So right, so let's suppose we believe that statement and try to see why that gives change on the equivalence given this plane. And nothing's going to change up until the Ci plus 1, Ci minus 1. Dot. Now I have the same Ci plus 1. Ci prime is no different. And I have the same Ci minus 1. But I have different, here's boundary I plus 1, boundary I plus 1 prime, boundary I prime. Okay. And I have to construct the map here is going to be the identity in both directions, identity in both directions. And the map here is going to be the identity, so I'm going to think of this as, you know, it's sort of something that's called E plus P equals Q. And then this is going to be E, same thing, E plus the same P plus Q prime. So E is just everything else, just a random letter. And then, so the math I want to do here is going to be in this, right, in this direction, I wanted to send, it's just going to be the identity on E plus P is going to go to P. I mean, I could just identity on E plus P. And then it's going to plus the map that sends Q to, what I want to do is say Q prime equals P plus Q. So if I say Q prime equals P plus Q, then what do I want? I want a map that sends, maybe I should say the other, going this way, it's going to be a map that sends, I'm not going this way well. So let's do the one going this way. And that sends Q prime to P plus Q. And actually that just has a natural inverse. And then the other way is actually just, in this case, all the maps are, all the chain maps are actually invertible. Okay, so this map that sends Q, it's just the change of basis matrix, right? And so this is just the, then going the other way is just the inverse. Okay. So once these are all invertible, so the composition is going to be the identities. So once we know these are actually chain maps, there's nothing further to do to show their chain homotopy equivalences. Okay, so the hard part is showing, if there is anything hard at all, is showing that these that all the diagrams, all the squares commute. And there are two squares to do here. But I claim that, I mean, I won't even do it, because I claim that this is, all of this, mess I made of trying to explain what happens with these boundary maps is just simply exactly what happens if you take a basis for something and you change it by adding, by making a new basis element, which is you replace Q with P plus Q, which is what we've done. Then how did you change your if you have a linear function mapping into that vector space, then and you change the basis in the target space, then you change that matrix by adding a row to a row. If you have a linear function going out of the space and you do this change of basis, you change it by adding a column to a column, which is exactly what we did here. So that basically all they're really saying is that boundary I plus 1 prime and boundary I prime are precisely are the only things they could be that make these diagrams commute, given this change of basis. So this is just a change of basis. Okay, so therefore these diagrams commute, and some of them modulo the actual geometry. And so now I want to prove this claim, that's the actual geometry we do. Okay.
So can I ask you a question? So
Yeah.
I'm not sure. So we do the birth deaths,
Yeah.
then somehow it seems more obvious to me that the right chain map is just the thing that sends this new guy you've added to 0,
Yeah, right.
and vice versa.
Right.
But I mean, I guess I see that this is sort of the obvious thing to do.
Yeah.
But like, why? Like, how do we know that it's really the chain map really is just summing these two generators?
What I'm trying, I think that if you believe, maybe the geometry will make it a little clearer, right? I mean, the point is that when you do a handle slide, you literally do you really do sort of see that the new Q prime is naturally the sum of the Q. It's naturally the original Q plus P. You picked up right? So let maybe start with the simple cases that we sort of understand well, right? So let's do an example before we try to do it in full generality, which we'll do a case, a three-dimensional case, right? And so so suppose we already are in sort of try to do a Hagar splitting type picture, right? So I want here's alpha curves. So these are alpha 1, alpha 2, alpha 3. These are ascending spheres for index 1 critical points. Okay, we're gonna handle slide in index I equals 2. Okay, those are ascending spheres for. So these correspond to the I minus 1 critical points. And so those are going to be the outcome of the output of boundary, right? And now let's draw some. Simple. Let's do something like this. So there's beta 1, beta 2, and beta 3. So those are the descending spheres for 3 different index 2 critical points. And let's not forget the descending sphere for the index 3 critical point, which, where is it? The descending sphere for the index 3 critical point, well, it actually runs into all these index 2 critical points. So index 3 critical point in dimension 3, its descending sphere is an S2. It gets punctured by the 3 different index 1 critical points. So then it should become a 3 punctured S2. But each puncture then gets compactified when you flow below to boundary, actual circle boundary components. So it should become a sphere with 3 open disks removed, with 3 boundary components. And that sphere, if I drew my things carefully, if I chose my circles carefully enough, should be this torus minus these 3.
Don't you want beta 3 to intersect? Don't you want all the beta curves to intersect the alpha curve?
I don't necessarily need that. I was actually trying to do. I mean, I could do something I'm more certain of that definitely will work. But this is that's going to give me S3 if you want it to be S3, right? And they don't have to, right? The only thing is the alphas have to be disjoint, the betas have to be disjoint, and the other key thing is that when you cut open along these, when you cut open along these, the betas, you should get a punctured sphere. Actually, no, I said something wrong. Okay.
You get 6.
Yeah, so why are we getting 6? The 3 sphere is, the 3 handle, the index 3 critical point, has a descending S2. The index 2 critical points have ascending S0, ascending,
okay.
right? Flipped upside down, they're index 1s. Their 1 handle is going up, right? So they have 2 points that go up towards. And each of those points has got to hit that S2 boundary of the 3 handle. So that S2 boundary gets, that S2, a descending 2 sphere from the index 3 critical point gets punctured 6 times. So it gets 6 boundary components when you go below and compactify. And those 6 boundary components are the 2 different sides, right? So it'll come in here and here, right? And so I claim that this genus 2 surface can be thought of as the image of a 6 punctured sphere with boundary components glued together, right? I mean, it's a funny way that I've drawn it, but I think that's all you really need to check is that that none of those circles separate. The whole thing isn't disconnected. Right? Anyway, so that's fine. But let's do a let's do a particular. So at the moment we have a chain complex that looks like. I mean, this is worth doing an example. Although we haven't done it, for example. So I have C3, C2, C1, C0. C3 just has a single generator, we'll just call it A. C0 has a single, A, let's call it D. And we call this E, single generator. And then this has generators alpha 1, alpha 2, alpha 3. And this has generators beta 1, beta 2, beta 3. Okay? And then the boundary map here, well, what is the boundary map? Now, what is this boundary map? Well, this descending S2 hits each of the ascending spheres with 2 points. But remember, we're counting with sign, right? And so they'll actually be opposite in opposite orientation. We're supposed to orient the ascending manifold, which is an arc, right? So you orient it, and then those 2 endpoints will have opposite sign. So then this is actually the 0 mark. Okay, does that make sense to everybody? And actually, the other way going down here, we'll have these the alphas will have these descending arcs, descending one discs, which will come and again hit the ascending sphere. So that boundary map is 0. So this is the only this is why this is a slightly misleading example, because we don't have 2 non-trivial boundary maps to look at, see from both sides. Okay, but anyway, we do this and we can so what's this boundary map? This boundary map, let's actually do the matrix. Well, it's just called boundary. And so boundary as a matrix should be a 3x3 matrix, okay? And we should have we should be looking, the columns should correspond to the betas, and the rows should correspond to the alphas, and each entry should be, so boundary of B1, boundary of beta 1 is just 1 times alpha 1 plus 0, so it's going to be 1, 0, 0. Boundary of beta 2 now is 0, 1. Well, okay, orientations I suppressed here,
But
right?
you're giving them orientation.
I'm giving them orientations by calling them wards, right? And then boundary of B3 is 0, 0, 0. Okay, does that make sense? Now let's do a handle slide. Let's slide beta 3 over, let's slide beta 3 over beta 2, for example. And so I'll just draw a parallel copy of it. Actually, this is important. This is useful to keep the beta 3 in there and draw the new beta 3 prime. Parallel copy. But what I emphasize there is that you really should sort of add beta 2 to beta 3. This is your new beta 3 prime. Okay. And what did you do? You picked up precisely these 2 new critical points, right? So you get this new prime, and that's 1, 0, 0, 1, and 0, 1, 1.
And if you had anything, it would still be there.
What's that?
If that
No,
column would
and
be
if you
there,
had, right. So now we can do another slide, right? Just like this, right? If you had anything, it would still be there, right? So all you did is you picked up all the stuff that the original one had, and that's it. Okay. Now, you might be satisfied with that, but that sort of is just what happens in full generality. By this example, I think I will try to sort of point out why it works in arbitrary dimensions. But let me point out one thing, which is that if I can convince you an argument, if I can give you an argument for what happens, that this is what happens for the outgoing boundary map. I claim that I don't want to bother with the incoming one, and all you do is flip things upside down, as always, right? You flip things upside down, that transposes everything, that changes, descending into ascending and so on, you'll have the same result for this, okay? So we just do it, we're just going to prove this only, right? Do this only. And the other one, this follows by extending ahead. Okay? And by the way, I mean, so, this example is just points out that if you ever want to compute the homology of a three manifold, and you have a Hagar diagram, it's incredibly trivial, right?
You're just counting.
You just count intersection points, and you get this matrix, and that's it. So if you haven't seen that before, that's nice one. I mean, the same thing is if you have a Handel diagram for a four manifold, well, computing the boundary of the boundary from index 2 to index 1 is, the Handel diagram of four manifold will show you, balls for the one handles, right? And then two handles that run over that, just to count the number of times they run over the one handles, and that's the boundary. What's harder is you typically can't see the three handles because they're hard to draw, and so that part of the boundary now is hard to compute from. Okay. So this is an attempt to generalize this picture to arbitrary dimensions, so we have our critical point in index Q, our critical point in index P, and then down below it all, we have lots of critical points of index I. These are both index I, and here's all these critical points in index I minus 1. And what we care, so we have a descending manifold here that runs into stuff. Oh, let's do it like this. Q is a little bit displaced to the side, and then Q is going to just move across there and slide on the P somehow. And so what I want to do is so now, as usual, we have to make a judicious choice of which level set we want to work in to see all the intersection points. And probably the nicest level set. I think the best level set to work in will be below P. Okay. So let this be our information Y. And so there we see, so in F inverse of Y, we have the descending manifold for P. I'm not going to write intersect with F inverse of Y. Anytime I'm in that level set, that's what I mean, right? So it's really a sphere, right? And the descending manifold for Q, they're both are both S spheres of dimension I minus 1, right? And then the ascending and then we have the ascending manifolds. Whatever these are called, these are A's, A, K, AJs, or whatever. The ascending manifold for the AJs are spheres of complementary dimension, n minus, there makes I minus 1, n minus I minus 1 minus 1, which is just I. So those are complementary dimensions, they intersect with points, and so we have to draw something schematic. So we have descending sphere for Q, descending sphere for P, and then we have, now what I'm going to do is, so we have the various ascending spheres coming and intersecting. They intersect the points, so these are ascending spheres for AJs. And they also some that come through and intersect here. Right. And now maybe it's time to, I remember one of the homework problems was to figure out how to sort of fully generalize what happens with a Hammond slide. Okay. So we can sort of maybe quickly talk about that and talk about it more next time. I claim that exactly what happens with a Hammond slide is that this is a um, you find inside the level set down here a SI with 3 balls removed. Okay, this is my point. So, which can also be thought of as a SI minus 1 cross an interval with ball removed. So, endless line gives Q prime, where the descending manifold for Q prime intersect where in F inverse of Y, the descending manifold for Q prime union the descending manifold for Q union the descending manifold for P is equal to the boundary of a I'll describe it this way, equals the boundary of an SI minus 1 cross 0, 1 minus an open ball. And of course, a sphere cross an interval is a sphere of 1 higher dimension minus 2 balls. So you can just as well think of it as this is also equal to the boundary of a SI minus 3 open balls. So the point is that, so you can see an example here will be that I have something like this. So the space in between here is this. That's what I want to say. So how do you see why this is true? We'll talk about this maybe on Monday if you don't have time, or you can think about this. So again, the point is you have up here you have this descending sphere, and then sometime it gets punctured, right? And it runs as we vary the descending manifold, the gradient-like vector field, it runs into the ascending manifold for this other critical point, and then it cuts across it, and so we puncture that point where it cuts across it, and then we flow that puncture down, and that gives us sort of a parallel copy of this beat, right? But then the point is, then you can count. All we care about now is that here's this manifold with three sphere boundary components. Okay, and then here's all these. Let's say something over there. So then. So we just have we have in F inverse of Y, we have embedded. Let's just give this thing a name. Let's call this whole thing equal to n. Okay. We have n is embedded in F inverse of Y. We have 3 boundary components. And so the signed count of the intersection. So then we look at, we'll consider n intersected with. What we want to do is understand n intersected with all these ascending manifolds, right? Intersected with the union over all AJs. Those are the critical points of index I minus 1. The ascending manifolds would be AJs. What's the dimension of this intersection going to be? N is 1. N is the boundary of n are the descending manifolds for the boundaries of n are the descending manifolds for this dp, dq, dq prime. So they intersect. These are complementary dimensions, right? And also dq prime. But now I've thickened it up. N is like a thickened up version of that. So it's going to intersect these guys in 1 manifold's arcs. Okay, because it's going to come through here. It's like 2 points there. So again, just because this is dimension I, this is dimension n minus I inside of n minus 1 manifold. So it's good. So this is 1 manifold, compact. We don't have to compactify anything. It's just a nice compact 1 manifold, right? Nice compact 1 manifold connecting all the intersection points between connecting these points, and the outer intersection points. So then it's a quick calculation by, it's really a coordinate, this compact 1 manifold is a coordism from the, I'm gonna say dp intersected with I'm just gonna say A's, union dq intersected with the A's, to dq prime intersected with the A's. So it's a coordism from a bunch of marked points to a bunch of points with pluses and minuses written on them, to another bunch of marked points with pluses and minuses written on them. And a coordism, if you count up the pluses and minuses, is just literally amounts to adding the pluses and minuses. So then you just add them in that time. So why is it add? In other words, I claim that this, anytime you have a coordism from an oriented zero manifold to another oriented zero manifold, then the sum of the signs on this oriented zero manifold at the bottom equals the sum of the signs on the oriented zero manifold at the top. And that's the proof. So once again, classification of 1 manifolds. That's critical. All right, exercises Monday.